Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
Okay, after starvation, the next topic is the classical problems of synchronization. Generally, whenever we discuss about the synchronization, right, we'll see a lot of concurrency related problems which deals with the control. Okay, so what we are going to look now is the concurrency control problems. So these problems are usually used for testing any newly proposed synchronization problem. Because whenever somebody says that, okay, I have a solution for the synchronization issue, these problems are given as the test cases for those solutions, and we'll just check that whether the problems are getting solved or not. Okay, all right, so the general way is like this. Okay, so fine, let's start with the problems one by one. The first one is called as, this is the first standard thing. It is called as it's a bounded buffer. So when you say it's a bounded buffer problem, uh, how powerful is a synchronization primitive? If you want to check that, we always go ahead with the bounded buffer problem. Okay, so uh, let us assume that there is a pool which consists of n number of buffers. Each is capable of holding one item. Okay, now if we use a mutex semaphore that provides, right, mutual exclusion to access the buffer pool, it is initialized with the value 1. Okay, you have mutex semaphore, we know that. Let us say that we have a mutex semaphore to provide the access to such buffer, right, and it is initialized with the value 1. Okay, so what is bounded buffer, we'll see now. Fine, let there be a pool of n. N is the number of buffers. Okay, each capable of holding one item. Now, so we are going to use a mutex semaphore. Okay, so let a mutex semaphore, right, is used to provide, let's say, provide mutual exclusive uh, access to the pool. Okay, so in order to access the pool we have a mutex this thing, comma, let's try to initialized to value 1. Now let us say that if you have a empty and full, right, there are two more semaphores, say one is empty, one is full. They count the number of empty and the full buffers. Okay, so buffer, in the buffer we have n number of buffers, so we use two more semaphores, say the name is empty and full. Okay, those are used to find out the total number of empty buffers and the full buffers. Okay, so the empty and full, so they are the names. Okay, empty and full uh, semaphores are used to count total number of buffers that are empty and full respectively. Okay, so we measure it using them. Now at the beginning you know that semaphore is, the empty semaphore will be initialized with n because we don't have anything filled, everything is empty. Okay, and the full semaphore is initialized with the value 0. Okay, that's obvious. Right, now let us say that we have a producer process, right? How to deal with this empty and full semaphores, providing access for the bounded buffer, right? We'll do this, we'll check this now. So let's say initialize let's say initialize the empty equal to n and full equal to 0, right? This is obvious because initially this is the condition, everything is empty, nothing is full. Okay, now let's go for the producer process. The code looks like this. Do, it's a do while statement, so let's write in this way. So you are trying to produce, it's a producer process, so produce an item, right? So this part of the code is responsible for producing an item. So producer consumer example we saw earlier, now we are trying to resolve the issue we faced over there. Okay, so produce an item, then you go for the wait function, wait empty, then also wait the mutex. All right, now next part is, after wait we can go for the one part which actually access the common variable. So that is, I'm trying to increase the number, right? How do you do that? You can do that by performing add the next part, I'll write next p to the buffer. See, we had a buffer earlier. From the buffer you used to add something and you used to take out something. So when you add something, others should not be able to take it out because you had a problem with it, right? So that's why we are trying to solve it now, right? After I do this, After you finish the adding process, now you go for a signal. Okay, signal, first you perform the mutex. Mutex is responsible for accessing the buffer, and then you go with the full. So this is signal full. You are incrementing that because, right, that's how it is done. So now let us try to close, and this is while say true. So we know that using this technique we are not allowing the other processes such as the consumer process, right, to access the buffer uh, when the producer process is accessing that. Okay, so there is a symmetricity between the producer and the consumer. The interpretation between the producer is producing full of buffers and the consumer is consuming the product from the buffer, right? So that's how the buffer was placed in the first place when we discussed the first part. Okay, so this is the example how the using semaphores we are trying to solve the issue. Okay, so this was the first part, which is nothing but the producer process. Now we go for a consumer process. So the consumer process, first we will have the it's also a do while, right? So first we'll do the wait, because right, whenever we are using a wait of something, I need to do the wait part of the other thing over here. So signal is called here, so I have to finish this with a wait at the first on the other side. So this is wait of full, then wait of mutex, right? Then we have the code which accesses the buffer, right? In order to access the buffer, we know that, right, the producer process should not be accessing that. So the first two lines will make sure that okay, it has been done. So the producer process has placed the item on the buffer. Now you can access that. So how do you do that? You can write a code that is corresponding to remove an item from buffer, right? This part of the code is responsible for that. Then I'll do the signal part. Okay, this is signal, because signal is responsible for reducing something. Okay, and we'll do the signal of this is empty. Right, now if you have any other process after you want to execute, which is after the removal of this, you can write here. Let's try to write a part of that is a consume an item. This is the one which has been removed from the buffer, right? After that, let's try to close this and finish the while loop. Do while loop, while true. All right, so the interpretation is very straightforward here. Producer is producing buffers. The producer is always trying to fill up the buffer. At the same time, the consumer is right trying to produce an empty buffer, right, from the producer. Whatever is the producer is producing, the consumer is trying to take out everything from there so that it can produce a empty buffer, right? By using the semaphores, now we understood that, right, the bounded buffer problem which we had at the first place has been resolved. Okay, so this is the first problem, and the first problem by using the semaphore we are able to solve, right? Then the second major problem which is commonly used in synchronization is called as the readers and the writers problem. Right. Let us say that you have a database and it has to be shared among several concurrent processes. Right. Some of the processes are they just want to read the database, let's say, and some other processes may want to update, in the sense read as well as write. So two things you have. Now, in order to distinguish the types of processes, right, referring to a database, we'll call it some as just readers and some others as writers. Okay, so let's write that in brief. When a database needs to be shared among concurrent processes, right, we basically have two things happen. The first one is called as a reader. It's called as a reader process, right? Processes who want just to read, processes which only read the database, right? Whoever just reads but not performing any write operation, it's called as a reader, right? And there is another type of process, it's a writer. So the writers, right, want to read as well as write, so we call it as the processes which update, right, update the database. It can be a value of a particular cell in the whole structure, or it can be a whole row in a table or column in a table, etc., right? So mostly, right, whoever performs the updation of operation, we call them as writers. So if two readers access the shared data simultaneously, we have no problem. But if a writer and some other, right, reader or writer is actually accessing the database, then, right, there may be a problem. So two readers accessing the same thing simultaneously, no problem, right? But when one reader and any other, one writer and any other thread, any other process, if it accesses that, then you have a problem. Okay, if I don't write when there is no problem because it's understood, they're just reading it out. No issues. Then nobody will update. But if one writer and sorry, and say any other process. So here any other we are referring to reader or writer. Okay. Access the database simultaneously, right? If at all it's happening simultaneously, right, this means, right, there is a problem, right? The same problem which we had discussed earlier. So now, to ensure all these difficulties we discussed so far that do not arise, right, we require to have a specific condition on the writers, right? That is, whenever a writer is accessing the database, right, it has to be an exclusive access, right? So we'll write in short now. So this implies This implies writers need exclusive access to the shared database. Exclusive because when it is accessing, nobody else should be able to access, because we just saw that there will be a problem, right? So the synchronization problem associated with this type of issue, right, is called as readers writers problem. Okay, so now let's say that though we discussed this as a very simple issue, right, there are actually different versions of the issue, right? This read writer problem has several phases. Okay, so let's look at the different phases now. The first one is called as first read write problem. It's called by the name first read write problem, right? So here the idea is that no reader will be kept waiting unless a writer has already obtained the permission to use the shared object, right? No reader should wait for other readers to finish. Readers should not wait. This is the first issue. Like whenever you design something, maybe the design requirement is this. You don't make any of the readers to wait. No reader should wait. This could be the first issue. Let's write that. Okay, so here no no readers, or no reader, let's write it. no no reader should no reader should wait for other readers, for other other readers readers say finish. We can put it in this way: no reader should wait for other readers to finish. Okay, simply because a writer is waiting. Okay, this could be the first thing, right? Here uh, you are not going to keep a reader to wait unless a writer has already obtained permission to use the shared object, right? When some writer has already got a permission, until and unless there is a permission to a writer to access the database, you will never make a reader to wait, right? As soon as reader wants, you give a permission. This is the first type of scenario, right? The second thing is that the next problem, let's go to that. This is called as the second read write the second read write problem. So if a writer is waiting to access the object, no new readers may start the reading. This is a different version of that, right? So writers here, once a writer is ready, writer performs its write operation as soon as possible. That's the second version of the statement. So I'll write the easier one. So if a if a writer say is if a writer is waiting to access to access the say database, then no new readers may start the reading. So reading should not be possible under this condition, right? So if it now you see that if at all you try to give a solution to either of these problems, right, there may be a condition, right, ultimately which results in starvation, right? We know the starvation, one of the object is not getting a chance at all. So what happens? Look at the first case. The first read problem is going to result in writers end up starving, right? Because readers keep coming, writer is not going to get a chance. Writer will keep waiting over there, so that the solution to the first problem results in the writers starving now. At the same time, the second case you see here, right, it says that the writer is waiting to access means readers should not be allowed, so readers will end up starving. All right, so both problems have their own uh, issues related to the starvation, right? So we'll write that point here. So this is first problem. Whenever you try to give a solution here, right, what happens? Writers may end up starving. So there is a starvation for writers. At the same time, if you try to give a solution to the second problem, right, we can see that the readers may starve. Okay, so we try to give a solution now for maybe, right, the one of the solution is fine. So just let's try to solve the first readers problem now, right? The reader processes share, right, a given data structure. Let's look at a data structure that is a solution for this problem. Okay, uh, so let's write the solution to the first problem. So here, let's create a data structure that reader processes will share. Let the reader processes share a data structure, right? That is, it's a semaphore. Semaphore. One is mutex and one is WRT. It's a writing. And then we also use an integer. Sorry. Okay, this is int, integer variable to have a read count. Okay, now so how to begin the solution? Let's say that the semaphore, it's a mutex and WRT. Let's say we try to initialize both of them, right, as say 1. Let mutex and WRT both are initialized to 1, and there is a integer value, that is read count is equal to 0. Let's do this. Now, the semaphore, which is WRT, is common for both reader and the write processes. Okay, the WRT will be shared with the write processes as well as the read processes. But let us say that mutex semaphore is used to ensure mutual exclusion whenever the read variable read count is updated. You see that we use a semaphore mutex just to provide a mutual exclusive uh, access for the variable read count. Whenever a process is updating the read count, we use a semaphore mutex just to provide uh, what you call mutual exclusion. Okay, so let's define that now. Uh, the WRT is a common semaphore for read and write processes. That's the first thing. And we try to provide another feature here, that is mutex. So one is WRT, one more is mutex, right? Is a semaphore used to provide mutual exclusive access when the read count, this is a variable, is updated. Whenever a write process updates this, we are trying to provide, right, a mutual access to this. That's the importance of this. Okay, now let's say that we have a read count variable. This keeps track of how many processes are currently reading a given object, because the name says that it is read count. There is no problem whenever processes are reading something, right? Because multiple can read something, only somebody is updating that or writing that, then we have a problem. Okay, so let's just define what this read count is actually doing. All right, so the read count uh, is a variable to keep tracking how many processes, out of all the processes, how many processes are currently reading the write object, or it can be the database. Okay, how many are currently reading? So the semaphore WRT functions as mutual exclusion, right, semaphore for writers. That's why the WRT is used, right? We understand that. So fine. Now let's look at the writer process, how the writer process provides a mutual exclusion. Okay, so let's look at a writer process. So start with do while do. Initially I need to wait function, go with WRT process. Right, so this means I can do which process? I can do the writing. This is the writing is performed here. We can write a code now, because we are saying that okay, we are doing a write, nobody can access. right? Now you can go for the writing. WRT can be increased now, so because it was reduced earlier, now you can increase this, right, by providing signal of WRT, right? So, and we'll close this and we'll say while true. So you can see that, right, the writing, before doing the writing process by any writer who is going to perform a write operation, right, it will initialize the wait function first, right, and it will perform the writing operation, and once the writing operation is finished, it will indicate that by a signal operation. So what we already have studied, we are applying now. Okay, this is the writer process. Very similarly, we can actually go with the reader process. Right, so let's give an example of a reader process. It's also a do while. Right, we'll start with the wait. It's a mutual exclusive, so I have to start with that. Go with the mutex. Right, now I have to keep a count of how many processes are reading simultaneously. So what you do now, this is a particular process which is going to read, so we increment. This is read count plus plus. Okay, now I just have to check that if the total read count is equal to 1, right, read count is equal to 1 means one process is doing that. You can go with the wait option of a WRT. So let's write that. So if, right, the read count equals to 1, right, what I can do, I can go with the wait of WRT. Okay, then I can perform a signal operation. This is signal of mutex. Okay, now this means I can do the reading operation, right? So only after this we come to a step where we can perform the reading is okay. Then I write the explanation for this later, right? Now once this is completed, you do the reverse. So signal has been performed here, so once the signal is done, I just have to reverse it by performing the wait. This is wait mutex. Right, now once it is done, once you perform the reading operation, you should decrease because you are leaving now. This is so read count minus minus. Okay, now once again I will check if the read count is equal to 0. I can actually perform the signal of mutex, signal of write WRT, right, because the WRT function I can actually write do an increment in that because it's done now. So if I'll go with another if condition. So if read count equals to 0, I check the condition and I update the signal by doing a signal operation of WRT, indicating that nobody is reading right now, so which means the write function can be increased and somebody else can do that. Somebody else can access that, some other writing process can access that and update it. Okay, so that's why this is the signal. Then we'll go for signal mutex. So that finishes this. Then we'll write while true. So the write function is actually acting like a mutual exclusion semaphores for the writers. Somebody is writing means we can do the uh, operation related to the WRT semaphore. So we can see in this code that it is the WRT is used by the first. It can be the first or it can be the last reader that enters or exits the critical section. Whichever the writer enters or leaves the critical section, right, will update the same thing. Okay, now I also understand from this code that it is not used by any reader who enter or exit while other readers are actually in the critical section. That doesn't matter, right? So now we, what in general we understand from this code is that, right, let's try to write few points about this. So if a writer is in the critical section and n readers are waiting, what happens here? One reader is queued on the WRT and n minus readers will be queued in the mutex. This is the solution. What's the solution you're providing now to the problem? This is a particular solution, right? That is, so if a writer, if a writer uh, is in the critical section, if some writer is in the critical section and let's say there are n readers, they are waiting, then one reader is one of the reader is going to be queued on, let's say, WRT. This is the first semaphore, and the remaining, how many are remaining? That's n minus 1. N minus 1 readers are queued, they are going to be queued on the mutex. That's the meaning. That's the solution which we are giving. Right, now we observe one more fact from this code. Let's say there is a writer who is executing the WRT's signal operation. Under such condition, we can resume the execution of writing, maybe sorry, not writing, the readers or single writing writing. So writers can execute whenever readers can execute their operation whenever a writer is performing the signal operation. This is the other point which is clear from the uh, code. So the solution consists of all these points. When let's say a writer, when a writer executes signal of WRT, so this means it's that WRT function is the semaphore will be increased. It means others can perform the job, right? So whenever this happens, I can write, we can resume execution of waiting readers. Either execution of readers are possible or a writer. So readers or writer. Okay, now the read writer problem, there are multiple solutions to this, but this one particular solution is considered as a very good solution. Okay, because other solutions are like by using some mode, lock, etc. Right, you will provide the read or the write operation, right, dependent on multiple conditions, right? So those conditions, monitoring of the condition, you need more variables or more semaphores. Holding them will be difficult. That's why without using any lock or any monitoring condition, this particular solution gives a uh, uh, easy answer to the problem. Okay, that's why this solution is considered as the most dominant solution to the problem. Okay, so that's the problem of read write solution. Then let's go ahead, and the next problem, this is the problem number 3 faced in synchronization, is called as the dining philosopher problem. Okay, so assume one condition, right? This kind of problem arises whenever we are designing OS having concurrent execution of the processes. Now, so instead of talking about the processes, let's think that there is a table, there is a round table, and consider there are 5 different philosophers. Always they think while eating, let's say. Okay, so the philosophers share a circular table surrounded by, maybe it's like the table has 5 chairs, each belonging to one philosopher. All right, so uh, let's write a diagram over here. So there is a table, round table, and let us say that we have maybe some tables. Maybe this is 1, 2, 3, 4, 5. Okay, and we have some chairs. 1, 2, 3, 4, 5. So the idea here is that at the center, let's consider that there is a bowl of rice. Okay, I'll draw this thing. This bowl has the rice. Okay, now the idea is that you every on the right side of everyone's plate, you have a single chopstick. So you can see that this is a chopstick. So everybody gets one chopstick. Okay, there are total 5 chopsticks. All right. So the problem is this: when a philosopher is thinking, because it's a problem of philosophers, they are actually eating and thinking. So whenever a philosopher is thinking, right, uh, that philosopher is not allowed to interact with others. Somebody's thinking means they do not interact, right? So whenever they think, right, philosopher gets hungry and tries to pick up 2 chopsticks which are closest to the particular philosopher. For example, whenever, say, there is a philosopher, this philosopher wants to eat that philosopher tries to pick up these two, and so that they can borrow the rice to this. Okay, that's the idea. Whenever somebody is hungry, they will try to pick up two chopsticks which are located nearest, only nearest, others cannot be accessed, right? But at some time you may find out a situation that a philosopher may pick up only one chopstick at a time because other one is not available, possible, right? Now it's because a philosopher cannot pick up a chopstick that is already in the hand of a neighbor, right? For example, whenever this philosopher has taken these two, so if the neighboring philosopher, that is this philosopher, wants to pick up, means he or she can take up only one because other one is already occupied. So it's a problem related to the total resources available. Finite number of resources are available, and you have more number of uh, demand for that. Okay, so let's continue the problem. Problem is not at over. Now, when a hungry philosopher has both the chopsticks at the same time, right? That particular philosopher can eat without releasing the chopsticks. In the sense, right? Whenever a philosopher is hungry, if the philosopher has both the chopsticks in hands, then they can eat rice. Okay, when that the hungry philosopher finishes eating, that philosopher will put both the chopsticks back and starts thinking again. So thinking means no work, chopsticks are free. Okay, at that moment the chopsticks are available for other users. So these are the overall conditions. Okay, now we'll relate this to what is called as the synchronization problem, that is related to the processes. When we have multiple processes, they are running, right, and there is a finite amount of resource, right, then we need to make sure that, right, the processes, right, how to handle, right, who gets the next chance, right, who will get the chopsticks here next, because once there is a once, say, this particular philosopher takes this, right, either this or this may not get a chance because only one of them may be free, right? So both of them will wait to get this. So if this is released, these two are released, then both of them will get a chance, like that. So we will be able to decide the solution of this problem, right, by using the semaphores once again, right, because semaphores are very good solution for the synchronization issues, and we will see, right, in the next class how semaphores help in solving this particular problem. Okay, by using the semaphores we will be able to solve this problem.
That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.